Hello everyone. Welcome to my course on the foundations of modern mathematics. My name is Casey Mann and I'm a mathematics professor at the University of Washington, Bothell. So this course on the foundations of modern mathematics is intended for students who are ready to take their mathematical training to the next level. So students who are coming into this course typically have had maybe a couple or three courses on calculus. And so by this point, you're getting pretty good with sort of algebraic manipulations and calculation. Maybe you've even had like differential equations or linear algebra, and that's great. The more you have, the merrier. But the purpose of this course is to move you from those type of courses where you're doing mostly calculation into the sort of more modern realm of mathematics where you're going to think more abstractly and more generally. And so courses like that would be courses like analysis, which is like the theory of what you did in calculus, and abstract algebra and topology. So maybe some of these words sound kind of familiar, but you don't know much about it. You're looking forward to learning about it. That's what this course gets you ready to do. One of the big goals for this class is that students learn how to prove mathematical statements. And so there's a lot that goes into doing proofs. And some of the secondary skills involved in this are things like, learning how to think logically. So we're actually going to approach logic somewhat formally in this class and learn how to use it as a tool to shape your thinking and also to give you techniques for proving things. One important skill that you learn in this class is how to digest mathematics. You know, mathematics often comes in these very abstract forms. So you're given definitions of things, for example, and the definitions might be kind of general and abstract. And so you have to learn how to internalize those definitions and associate them with concrete things so that they really make sense to you inside. Very important skill. Learning the language of mathematics. So in mathematics, we kind of have our own way of speaking, our own way of writing, and we certainly have lots of symbols that have specialized meaning. And you have to learn, you have to get accustomed to those styles and those symbols so that everything doesn't look like gobbledygook. These things are very concise and have good meaning, but you have to get used to it. And one thing I think is important is learning to think abstractly and learn how to make generalizations. So a lot of the things that you've learned in your previous courses are very specific. Like when you're in calculus class, you learn a specific formula for how to do a derivative or to do an integral, things of that nature. But we want to move into the kind of mathematics that applies to a broad range of different topics. It's a very powerful idea. So moving from the specific to the general involves things like, let me just give you an example. In the subject of abstract algebra, there's a structure known as a group. And there are lots of examples in lots of different areas of mathematics. So if you go into analysis, the land of calculus, the real numbers and the complex numbers are examples of groups. But you can go into the land of topology. In topology, you've got certain kinds of groups. Like there's something called a fundamental group. There's homology groups. And these things all have different meanings. But the cool thing is that anything that you prove about groups in general applies to all these different special situations simultaneously. So that's a very powerful thing. So there's a lot of power in generalization and abstraction. So that's something that you're going to start, being more exposed to. And in this class, one of the most fundamental things that we talk about are sets. So everything in modern mathematics is based on sets, as we'll see. So that gives you a little taste of what this course is about. And so what I'd like to do now is to give you a motivational example. So I'm going to ask you to do something that I haven't given you any training for or any, knowledge, but this is just an exercise to kind of see what you'll do with it in the absence of having been told what to do or how to do it. It's kind of an illuminating example in that it makes you think about what you need to really prove things. So I'm going to ask you to prove something. So prove the following. Let's prove that if n is an even integer, then it must be the case that n squared is also even. So I would like you to take maybe however long it takes, but I would guess maybe 5 to 10 minutes. Sit down and think about how to prove this. And there's no right or wrong answer here at this point in time. Press pause now and try it. All right, so welcome back. And now that you've had a chance to think about this problem, let's talk about some considerations that probably occurred to you. One big consideration in doing a problem like this is definitions. So what do you mean by integer? And what do you mean by even? What do these words even mean? We have to, I think probably most of us kind of like have some sense of what an even integer is, like 2, 4, 6, 8. But we'll probably have different ways of sort of verbalizing like what we mean by even. So let's talk this through. So some considerations here. Well, so we'll spend some time developing sort of number theoretical definitions more thoroughly. But for the sake of, so that we can agree on something, the integers, and we tend to use this symbol, kind of a fancy looking Z, are this set of numbers that look like, it's like whole numbers with sign, can be plus or negative or positive. And what do we mean by even? It's kind of interesting to see what students come up with, but most people come up with something along the lines of, well, if it's even, that means you can divide 2 into it evenly. So oftentimes students come up with something like n is even if 2 divides it. If 2 divides n evenly. And that's perfectly correct, but it kind of pushes things down the line a little bit, because then you would say, what do you mean by divides evenly? And so then people start thinking, okay, well, then it starts turning into something like, well, if you take n and you do that over 2, well, divides evenly. If you divide evenly, that means that this fraction should be an integer, right? And this is getting closer to what we typically use for a definition of even. Here's what we're going to use. Definition. An integer n is even if there exists some other integer k such that n is equal to 2 times k. Now if you think about that, if you think about what this sort of intuition is right here, where n over 2 is equal to an integer, if you think about it, what we just wrote by saying n is equal to 2k here at the bottom is basically the same thing, right? We're saying if we would take that first equation, n divided by 2 equals an integer, and we called that integer k, then we'd have n over 2 equals k, and then multiplying both sides by 2, we end up with n equals 2k. You can see how your intuition would have led you to this sort of definition anyway. And what's nice about this definition is that it doesn't involve fractions, because fractions, as you know, tend to introduce complications. And so we tend to avoid fractions if we can. All right, so it's important in any mathematical course, we have to agree on some definitions. Now, it's also true that there could be more than one formulation of a definition, okay? In fact, you see this happen a lot. Like when you open up one math book, they defined, object X this way, and then you go to a different math book and they define the very same object using different words. But what you'll see is that those definitions are typically equivalent. So it doesn't matter so much what the definition is and exactly how it's worded. What does matter is that we agree on it, and we agree in this course that that's what we're going to use. And so this is what we're going to use for the definition of even moving forward. And I'm sure you've seen this in all your math books, right? Most math books lay out definitions of things, and then you just have to go with it. Unfortunately, there's not like some high council of mathematicians who decide what the universal definition for everything is, right? But it is important that the definitions that we work with across different areas of mathematics, that they have some equivalence, right? Okay, and then so now we know what integers are and we know what even means, and so we kind of know what the words in the statement are. Some other considerations. What are the basic things that what do we get to assume is true? I mean, we have to have some base of knowledge that we work from, right? In mathematics, we talk about axioms. So axioms, these are just assumed truths. So we have to have some basic things. You may have experienced this in a previous course. Most people in high school take a course on geometry. And in geometry, you may remember the postulates, the 5 postulates. So postulate is just a word that's synonymous with axiom. And so those 5 axioms in geometry are things like, given a point, given 2 points, there's a unique line that passes through those 2 points. There's like the parallel postulate, the one that says if you take a point that's in a given line and the point's not on that line, then there exists a unique line through that point that's parallel to the given line. There are a few others, I don't remember them off the top of my head, but they're really basic things. And they're things that seem like they're self-evident, and you have to build the rest of the theory off of them. Another consideration is what do you mean a proof? Like, what is a proof anyway? In different areas of science, what constitutes a proof? We have different standards. So a proof in biology is different than a proof in physics, is different than a proof in mathematics. Mathematical proofs are the least likely out of all the sciences that you're going to find out later that it's wrong. So, mathematical proofs are based on, accepted axioms and accepted definitions, and then logic. So logic is the key thing here that we need. Logic is what we use to justify our proofs. It gives our proofs sort of this ironclad quality. So unless they change the rules of logic, or we change the definitions, or accept different axioms later, what's a proof of something now is going to be a proof 100 years from now. So anyway, mathematical proofs are very ironclad. Unless the rules of logic change, or new axioms are presented or taken away, or something strange happens, something that's proven mathematically in 2021 is probably still going to be a proof 100 years from now, 1,000 years from now. On the other hand, things that are sort of proven in physics, they might change once, they may change over time. I mean, Newtonian gravity, for example, was, pretty well accepted, right? I mean, everybody said, yeah, this is, gravity works according to an inverse squares law. And then this guy Einstein came along and, developed a whole new framework for how we think about gravity. And who knows what's going to happen with gravity in terms of, quantum physics. They haven't quite figured that out yet. So, theories and things that are kind of considered settled in physics can be different over time. I mean, it might change, or it might be modified later. So anyway, we have different standards of proof. And, in biology, the way they would typically prove something is just, amass a lot of different specific pieces of evidence. Like, the theory of evolution is very well accepted among biologists, and they have tons and tons of evidence that support it, and they have 0 pieces of evidence that refute it. And that's the cool thing about science, is even if you got a great theory and you have a whole lot of evidence for it, it doesn't take but one strong piece of evidence to deny it. And the same thing happens in math, right? If we have some thing that we're wanting to call a theorem, all you have to do is present me with one example that shows that theorem is not true, and then that theorem's not true. I'd have to think about modifying that theorem to figure out what scope it is true. Maybe it's not true at all. So these are some things to think about when you think about proof. So let's take a look at this example a little bit more. So the example, I haven't done the example yet, but let me talk about some ways that I've seen people do this example. All right, so here's one thing I've seen students do. They might do something like, well, let's see. I know n equals 2 is even, and then if I square that, I get 4. Hey, that's even, so that checks out. And then let me pick the next even number, 4. Well, if I square that, n squared would be 16, and that checks out as even. The next even number would be 6. And if I square that, I get 36. Okay, that's even. Wow, it looks like to me this pattern's going to go forever, so that must be a proof. Of course, this is not really a proof because it doesn't really consider every possible even number, right? I mean, turns out we missed a lot of them. 3 out of infinity is still, we have infinity left to check. I mean, this kind of reasoning can be fruitful. Sometimes if you can establish a pattern, you can sort of capture that pattern and prove that that pattern always holds. But that's not what's going on here. And then closer to the truth I see people doing sometimes is, well, they'll say, if n is even, well, they might not know how to express it exactly, but they'll say something like, well, if you do 2 n to n, the remainder is equal to 0. And then maybe if they start to think about that a little bit, they'll get to the point where they'll say, well, that means n divided by 2 is a whole number, kind of like what we were talking about earlier. And then they'll say, okay, well then now you got to think about n squared. Maybe they'll take this thing and go, well, if we square both sides of this, we'd get n squared over 4 equals k squared. And then from there, you might say n squared is equal to 4 times k squared. And sometimes people might get stuck with this because then you need to talk about n squared over 2, right? So maybe they would go, okay, so n squared over 2 would be 2k squared. And if you realize that 2k squared must be a whole number, if k was a whole number, this is pretty close to the truth. It's just a little wonky in terms of like not knowing how to know when you're done. So let me give you what I think is sort of the good proof, the one that uses the definition we gave on the previous slide. So what I would do is I'd say, suppose n is even, then according to my definition, there would exist some integer k such that n is equal to 2 times that k. And now it seems really easy to manipulate this equation. I want to talk about n squared. So n squared is equal to 2 times k quantity squared, which is 4k squared. And I realized that I could pull a 2 out of that and write it as 2 times 2k squared, like that. And then let me observe that if k is an integer, so is 2k squared. So n squared is equal to 2 times q, where q equals 2k squared is an integer. Thus, n squared is even, because it's 2 times an integer. We usually like to put a little square at the end of our proofs to signify that the proof is completed. Sometimes people write this QED stuff at the end of a proof, which is also okay. But I usually go with a little square because I don't really speak Latin. All right, so notice how nice this is. It's very concise. I didn't have to deal with fractions, and I knew exactly like what I was looking for at the end in order to know that n squared was even. I knew because I had a definition that I needed to write n squared is equal to 2 times an integer, and that really guided my process. So having definitions is really important. So what I want to do next is give you another motivational example, but this one's going to be hard. And what it's going to point out is a need for some more advanced techniques. So let me give you that example now. Okay, so in this example, let's prove that for any integer n, if n squared is even, then n itself must have been even. All right, so I would like you to, just like last time, press pause on the video and take 5 to 10 minutes or however long it takes you to think about this problem and try to prove it. Okay, welcome back to the video. So I expect that you ran into some trouble here. In fact, I've been teaching this class for a number of years, and I've never seen anyone prove this unless they knew the trick ahead of time. And if you didn't know the trick ahead of time, congratulations. It's a really cool trick, right? But if you don't know the trick, if you just sort of proceeded in a natural sort of direct way, you'd probably try to do something like this. You'd say, well, okay, so if n is an integer, if n is an even integer, if n squared is even, then it must be the case that n squared is equal to 2 times k. That's the definition of even. So we have to somehow extract from this equation that n squared is equal to 2 times k, we have to extract from that something about n. And so when I think about this, the only way I can think of to extract any information about n from the n squared equation is like maybe to take the square root of both sides of that equation to get, like n equals plus or minus the square root of 2 times k. But then, man, that's complicated. I don't know what to do with that square root of 2. That doesn't fit into the definition of even very well. Maybe you could try to divide both sides by n so that you'd have n equals 2k over n. I'm feeling really stuck here with this. I don't know what to do. Okay, I think I'm just going to stop there and just say, you know what? I'm going to admit I'm stuck. Now I'm going to show you the trick for how we do this. Turns out we can do some fancy logic. And what we can do is convert this to a problem that's easier. You may have seen this in other classes before, these sorts of things. If you've ever had a differential equations course, there's a really cool trick where you're trying to solve a certain kind of equation, and what you can do is stuff that equation into this thing called a Laplace Transform, and it gives you a different equation. And if you can solve that equation, the new equation, then it tells you what the solution to the original equation was. We kind of want to do something similar to that here. We want to take the problem that we're trying to prove and sort of put it into a conversion box and get a new problem. And if we can prove that problem, it will simultaneously prove the original. Let me tell you how that goes. So one of the things we're going to do in this course is talk about logic, and that's kind of the point of this problem, is to point out a need for having fancy logic. So cool trick here. It turns out that the statement if n squared is even, then n is even is equivalent to this new statement if n is odd, then n squared is odd. And you might be going, what? How is that a possible thing? I mean, why on earth would this expression be equivalent to this expression? Well, it is true, and it is cool, but we'll save the why of it for later. But anyway, if you buy that these two statements are equivalent, then it turns out that the second formulation of these equivalent statements is much easier to prove. In fact, let's do that real quick. It goes very much along the lines of the previous proof we did. We do, however, have to give a definition for what we mean by an odd integer, but that's not too hard. So let's do that now. So a quick definition here. An integer, n, is odd if there exists some other integer, let's say k, such that our number n is 2 times k plus 1. Basically, the idea is that an integer is odd if it's one more than an even number, right? So if we accept this as our definition of odd, then we can prove the statement here, the second formulation, in a pretty straightforward way. So let's do that now. So our proof is, well, we'll start off by supposing that we have we'll start off by supposing that we have an odd integer. So suppose n is odd. Then we know by the definition that we just cited, there exists some integer k such that n is equal to 2 times k plus 1. And now we want to get our hands on n squared, so we're just going to take our expression for n squared, 2k plus 1, and square it and see what happens. And what we want to do is express n squared as 2 times some integer plus 1. Now, n squared is the quantity 2 times k plus 1 quantity squared, which we can then square out, and it'd be 4k squared plus 4k plus 1. And now I want to write that as 2 times an integer plus 1. And so the idea will be to gather those first two terms together and pull a 2 out of that. So I'm going to pull a 2 out of those first two terms, which would leave me with 2k squared plus 2k. And then I still have that plus 1. And then the idea here is that this expression in the parentheses is an integer, because k is an integer. If you take an integer and you multiply it by 2 and you square it and you add it to some other integer, you still have an integer. So what we're really making use of, without making it real explicit, is we're making use of what are called axioms of the integers. There are axioms for integers that says when you add two integers together, you get an integer, and when you multiply two integers together, you get an integer, and things like that. So, you know, we're kind of sweeping that under the rug for now, but I think it's believable that that expression 2k squared plus 2k is an integer, given that k is an integer. And so let's point that out. So I'll just say something like, note that 2k squared plus 2k is an integer, and if we let q equal 2k squared plus 2k, we have n squared equals 2 times q plus 1. So that makes it really crystal clear that n squared is odd, according to our definition, because I've expressed n squared as 2 times an integer plus 1. And that proves it. So isn't that cool? I mean, you have to be impressed by this. The original thing that we wanted to prove, that n squared being even implies that n is even, we converted that whole statement into a completely different thing to prove, and then we proved that new thing, and that proves the original thing. So this proof that we just did, even though we proved a completely different statement, we have now proved that this statement, the original thing, is true. If you're not a little bit amazed by that, or impressed a little bit, then I don't know, maybe this is the wrong class. But for me, that's really cool. And this is just one such logic trick that we can use. So it turns out that we're going to have a way of sort of thinking about mathematical statements in a sort of algebraic way that can be manipulated, and we'll basically have, like, you know, ways to simplify or rearrange logical expressions into equivalent expressions that sometimes make them easier to prove, or just simplify things. So this is a really cool thing that we get from logic. So, and logic is going to be one of our very first topics that we start covering in detail. This was just sort of to give you the idea of, you know, why logic will be important. Okay, so I want to wrap this lecture up by talking a little bit about what are the focal topics going to be for our Foundations of Modern Mathematics course. I think it will be a good idea to start with our basic logic. Logic is a very deep subject. You can do a whole PhD on logic, Foundations of Mathematics, but we're just going to cover the bare essentials that will allow us to start doing proofs. It really is an interesting topic, and you know, logic's one of the deepest areas of mathematics in the 20th century, I think. If you're interested in really pursuing it, I mean, you've really got to go read about Girdle's theorem, or what's it called, Girdle's Incompleteness theorem, which points out that any mathematical axiomatic system is always going to have some holes in it, statements that make sense in that system, but you can never prove them. They're sort of unprovable things. So that's really kind of cool. And that's interesting because back in the old days, mathematicians were really trying to come up with like this complete set of axioms that sort of covers all of mathematics, that any statement that you can make in mathematics, you can derive it from a set of axioms. But it turns out that's not possible. Anyway, and then once we have our basic logic down, we'll get into proof techniques. And just so that we'll have something really basic and something familiar to you, we'll talk about some basic number theory so that we can start proving things about numbers. Number theory isn't really going to be the focus of this course. We're just going to do a little bit of it just so we can start doing some proofs. But then we're going to quickly move on to the topic of sets. So sets are just collections of items that we call elements. It turns out that almost every general structure in modern mathematics is a kind of set. So sets are very fundamental, very foundational, of course. So we'll have to get used to dealing with sets, how to prove things about sets, basic properties of sets, and that sort of thing. And then one special kind of set is called a relation. We'll talk about those. It's a very hierarchical structure that we have in this course. Once we start talking about sets, everything's based on sets. So now next we'll have relations. So examples of relations are things like less than, or greater than or equal to, or one relation that two numbers could have with one another is that one number divides the other number or not. Two sets can have a relation between them. One set could be contained in another set. The list goes on and on of things that we can, different kinds of relations that one can have. After we talk about relations, we'll talk about functions. So functions are special kinds of relations. And of course, we know that functions are super important. I mean, that's all you dealt with in calculus class, right? So we definitely want to fit functions into an overall theory of things that's based on sets. And we will. And then the next thing we'll talk about, and this will probably end up being basically the last thing that we talk about in the class, are binary operations. Binary operations are one particular kind of function. So binary operations are things like, addition, multiplication. These are things you can do with numbers. If you're thinking about the land of functions, composing two functions is a binary operation. Yeah, there are lots of different kinds of binary operations that one can think of. If you go to the land of vectors, cross product is an operation on three-dimensional vectors. If you take two three-dimensional vectors, you can cross them and get a new three-dimensional vector. So things of that nature. There will be a few other side topics that we might get into, like when we're talking about sets, we may want to talk about countable and uncountable sets, and at some point we'll want to talk about a process called mathematical induction, which you can kind of think of as a kind of proof technique, and it really kind of falls under the number theory category, but we won't do that until a little bit later in the course. But basically this kind of gives you the hierarchical structure of the ideas of the class. At the most basic level here, we're going to have axioms, so things that we're going to assume are true, and we'll have definitions. So we just define what our words and symbols mean. That's sort of your lowest level in math. And then we'll use logic to derive things from those definitions and those axioms. You can kind of think of proof techniques as sort of part of logic, like an application of logic. And then once we have our logic and our proof techniques, we'll start proving things about sets. And then once we have sets down really well, we'll do relations, which are special kinds of sets. And once we have relations down, we'll do functions, which are special kinds of relations. And then once we have functions down, we'll do binary operations, which are special kinds of functions. And like I said, we'll have a few one-offs here, like mathematical induction and some things like countability. But yeah, these will be the big themes of the course. I'm really happy to be teaching this class. It's really one of my favorite classes to be teaching. It's just such cool stuff. It's really starting at square one and really developing and blossoming the big ideas in math that really lay the foundation for everything to come. In my opinion, this is maybe the most transformational course that you'll take. Certainly up there in the top 2 or 3. Just because what I observe is it really changes the way people think. So there are certain people who just sort of intuitively think very logically, and this stuff just is second nature to them. But for most of us, we need some training. And once you have the training to think very carefully about what the premises of your problem are, like what are you supposing is true, and then identifying what it is that you're trying to argue is true, and then realizing that you have to have a sort of a way to progress from what you're assuming to what it is that you're trying to argue that follows laws of logic. Once you start thinking that way and practicing doing your math that way, I think it even applies in real life more than you would think. We don't always think that way. Sometimes we're guided by what we want to be true. And scientists are susceptible to this kind of thinking. You know, you work so hard in the lab or whatever, trying to find evidence for something that you want to be true, that you start to like ignore evidence to the contrary and only pay attention to the evidence that supports your hypothesis. But in doing the kind of math that we do, it really does sort of train you to, you know, if you're trying to make this leap from here to here, why can you make that leap? And when you really make yourself justify each step, it makes your thinking a lot more clear, and it makes you less susceptible to making mistakes like that. Nobody's perfect, and I'm certainly not, but I think you'll see this class really does transform the way you think. And so I'm really excited that you're here, and I'm really excited to be part of this journey with you. So I think I'll stop there, and our next video will be on logic and proof techniques. Okay, talk to you soon. Bye now.